In the previous lessons, Introduction to Algorithms, we've just given some examples on how to write an algorithm in pseudocode using iterative or recursion methods, without discussing the fundamentals of problem solving. What we need now are the steps and guidelines that everyone should follow to design an algorithm that is accurate and more efficient. Here is a list that briefly describes a sequence of steps one typically goes through in designing and analyzing an algorithm. The first step is understanding the problem, followed by deciding on some of the algorithmic characteristics and features, followed by the design step. After that, proving the correctness of the algorithm, followed by analyzing the algorithm, followed by writing the code using a programming language. If we fail to prove the correctness of the algorithm, or after analyzing the algorithm it is discovered that the algorithm is inefficient, then either we go back and change the design of the algorithm, or we go back and change some of its characteristics or features to guarantee that the algorithm is correct and efficient. Let us discuss in details what we're supposed to do in each of these steps. The first thing you need to do before designing an algorithm is to understand completely the problem given. And you may ask questions if you have any doubts about the problem. In this step, you have to do a few small examples by hand, think about special cases, and compare the problem with existing problems, and whether the problem in question is one of them or not. Finally, it is very important to specify exactly the set of instances the algorithm needs to handle and what are their ranges. An instance of an algorithm is defined as an example of an input to this algorithm. Any value passed to an algorithm through its parameters is considered as an instance for this algorithm. For example, any two numbers passed to the GCD algorithm are considered instances to this algorithm. Or all arrays with different combinations of integer values are also considered instances to the reverse algorithm, and so on. After understanding the problem step, what are the characteristics and features that we have to discuss and investigate before designing an algorithm? First is the computing capabilities. When designing an algorithm, either the algorithm is designed to run sequentially on a single processor called sequential algorithm, or is designed to run in parallel or multiple processors called parallel algorithm. We will be focusing on only sequential algorithms that run on a single processor. Our next concern is whether to worry or not about the speed and the amount of memory for the computer that will execute the algorithm. For scientific exercise, the answer is not to worry, because the purpose of the exercise is to measure the efficiency of the algorithm. And this can be done without depending on any computing resources. However, if we want to design an algorithm for a real-time system, then we have to worry about the computer speed and its amount of memory, because time is critical. For some algorithms, either the output must be an exact answer to the problem or approximate. Writing an algorithm for computing GCD is an exact algorithm. However, writing an algorithm for computing the square root of a real number is an approximation algorithm. So an exact algorithm always produces an exact or optimal solution, but sometimes very slow. And for an approximate algorithm, it produces a near optimal solution in an accepted running time. Finally, you have to pay close attention to choosing appropriate data structures to the operations of the algorithm. As an example, for some algorithms, they run longer on linked lists instead of arrays, and sometimes the opposite. That's why algorithms plus data structures are fundamentally very important to computer programming. The algorithm design techniques, strategies, or paradigms are a powerful set of general approaches to algorithmic problem solving. Despite the availability of these techniques, designing an algorithm for a particular problem may still be a challenging task. Some design techniques are not applicable to the problem in question, and even when applicable, the task of choosing among the general techniques and applying them requires skills that need practice to get easier. Examples of these design techniques are brute force, divide and conquer, dynamic programming, and etc. In fact, these design techniques will be the axis of all algorithms that will be presented and described in the coming lessons. Once you have designed an algorithm, you need to specify it in some fashion. The two most widely used options nowadays for specifying algorithms are description by words in a free and also a step-by-step form, or by pseudocode, which is a mixture of a natural language and a programming language like constructs. We've already mentioned that pseudocode was usually more precise than natural language, because describing the steps of algorithms in words may introduce ambiguous instructions. But there is no single pseudocode that is agreed on by all computer scientists. Therefore, we will continue using the constructs that we have been using in the previous lessons, like for and while loops, and if for selection, and we'll introduce more in the coming lessons. In the earlier days of computing, flowcharts were the dominant methods used for specifying algorithms. But this representation technique has proved to be inconvenient for all but very simple algorithms. Once an algorithm has been specified, you have to prove its correctness. That is, you have to prove that the algorithm generates a required result for every legitimate input in a finite amount of time. For example, the correctness of the Euclid's algorithm for computing the greatest common divisor depends on the correctness of the formula GCD between m and n is equal to GCD between n and m mod n. Therefore, the proof of this mathematical relation is considered as the proof to the correctness of the algorithm. A common technique for proving the correctness of algorithms is to use mathematical induction, because an algorithm's iterations provide a natural sequence of steps needed for such proofs. It might be worth mentioning that tracing the algorithm for performance with a few specific inputs cannot prove the algorithm's correctness conclusively, even with lots of inputs. But in order to show that an algorithm is incorrect, you need just one instance of its input for which the algorithm fails. In the introduction, we've mentioned that there were two kinds of algorithms efficiency. Time efficiency indicating how fast the algorithm runs, and space efficiency indicating how much extra memory it uses. To measure the algorithm's efficiency, a general framework and specific techniques will be later presented. In this general framework, we will see precisely how to measure these efficiencies in details. Another desirable characteristic of an algorithm is simplicity. Unlike efficiency, which can be precisely defined and investigated with mathematical tools, simplicity indicates that the algorithm is easy to understand, code, and follow for tracing. Moreover, another desirable characteristic of an algorithm is generality. Sometimes it is easier to design an algorithm for a problem in more general terms. Consider, for example, the problem of determining whether two integers are relatively primes or not. I mean whether their only common divisor is equal to 1 or not. In this case, it is easier to design an algorithm that uses the general GCD algorithm to compute GCD between these two integers than test if it is equal to 1 or not, rather than designing the algorithm for the problem from scratch. Most algorithms are targeted to be ultimately implemented as computer programs. But when doing that, special care should be given to the code. It is possible that making the transition from an algorithm to a program is either incorrect or very inefficient. As a practical matter, the validity of a program is still established by testing. Even more important, test and debug your program thoroughly whenever you implement an algorithm. Coding the algorithm helps to analyze the algorithm time efficiency, especially if the algorithm is difficult to analyze mathematically. In this case, an empirical analysis of the algorithm is used to measure the algorithm time efficiency. So as a rule, a good algorithm is a result of repeated effort and rework. So the conclusion is, a good algorithm is a result of repeated effort and rework.